This is the most important part of your race car. Today I'm going to explain to you why I believe that to be true, and I'm also going to try and give you a little bit of a better understanding of how this actually works. So of course, most of you will already know that this is a torque converter, and also over here I have my Power Glide transmission, 169 first gear. I mentioned in the last video a little bit about that when we were going over starting line ratio, so check that out if you didn't catch that. Also, near the end of that video, we also talked a little bit about how a converter is affected by the rear gear. So that is something you should check out as well, but we're going to get more into how the converter works and why you need to have a properly spec'd one and why that is so important, and some of the benefits that you can get from having a well-built converter. So anyways, first of all, I want to say a huge thank you to Specialties. They made this possible, and I'm really excited to have them on board and trying to shoot for this 6-second pass, and then for all the stuff to come after that. We'll probably be going back to some 8th mile stuff. I'm sure we'll be into some no prep stuff, all kinds of things, and I'm really excited to be running their products. So huge thank you to them, specifically Pete Nichols over there. He is a really good friend of mine, and he has helped me out a lot, and I've made some really big progress in my program from having his help, and I wouldn't know anything that I know about converters if it wasn't for him, so I really appreciate him. Anyways, let's just get right into this. First off, I'm going to just go over some of the basic stuff, and I want to show you what you're actually doing whenever, I'm sure everybody that has installed a converter before has heard of, the rule of, you're supposed to have it drop in 3 times. Well, I want to show you what's actually happening when that's doing that. Also, stay tuned for later in the video. We'll get into some data logs and show you some differences there as well. So, but for now, we're just going to go over the actual physical side of the converter, and I'm also going to show you guys what the differences are between a loose and a tight converter, and just how that can benefit or how that needs to be handled. So anyways, first off, what you're going to see here on the converter is these little grooves right here. That's going to be for the pump in the transmission, which I actually have some pump gears out of the transmission right here. So these are going to be engaging right there, just like that. And then of course, when the converter spins, it's going to be spinning this pump gear in the transmission, which is going to be supplying fluid to the rest of your transmission as well as the converter itself. And of course, this is going to spin when the engine is spinning, and it's always going to be spinning with the speed of the flywheel. So will the pump in the transmission. Next up, the next thing down that's going to be engaging is going to be your stator, which I have a old stator here that still has the spragless piece in it that will engage on the stator tube on the transmission. So I will just go ahead and slide that on there. So that is the next piece down that's going to be engaging, and this is not going to be spinning on this because this is a spragless stator. If you had a stator with a sprag or a mechanical diode, then it would be able to spin one direction but not the other. But for most of the stuff, or for just about everything that I do, a spragless stator is going to be beneficial, so that's what I stick with. And then the next thing that's going to be engaging is actually going to be the turbine side of the converter with your input shaft. And we can just go ahead and pull this input shaft out of the transmission real quick and show you how that engages, and that's going to be the farthest back piece in the converter. So we'll go ahead and just drop this in here. And there you go, you'll hear that engage and drop in there. And now the turbine is going to spin independently of the rest of the converter. As I said, the stator is not going to be spinning in there. So you're going to have the pump spinning, of course, with the engine, and the pump of the transmission, as well as the actual pump side of the converter, which we'll get more into that in just a second. But the turbine side is going to be what is connected to the input shaft. And that is always going to, just spin with the input shaft. So you can actually have the pump side of the converter, or the actual, whole converter assembly spinning while the turbine side is not. I'll show you how that will spin independently of the rest of the converter. So this is, of course, going to be whenever you're on the trans brake, for example, your input shaft is not going to be moving while the rest of the converter is. So that's why it can kind of be hard to, get the RPM up. What you're doing is, you're holding one side of the converter still while the other side is spinning, pushing fluid into that side, trying to spin it. So then once you let off that trans brake, then of course it's going to spin that turbine side very quickly and accelerate your car. So anyways, I will go ahead and put this back in here. All right, so now let's get a little bit into how the converter actually works. I know I have thrown some words around there and explained a little bit. I may have confused you with the two different pumps that I mentioned. As I said, you have the pump in the transmission that you're going to be spinning, and that's going to have pump gears just like this. But there is also a pump side to the converter itself, and the pump side is going to be on this side that you can actually see on your side, the camera side of the converter, or the transmission side of the converter whenever it is installed. And as I said, that is going to be always spinning with the engine. It's always going to be the same as the engine RPM, of course, because you are mounted to the flex plate. And I will have some pictures here as well and point out where the pump is. So as you can see, there are fins in the pump, and those are attached to this side of the converter, and those do not move like some of the other pieces in the converter independently. Then your next piece in the middle of the converter, as I mentioned, is going to be your stator. And now this is not a Circle D stator or the stator that I have in the car right now. It's going to look a little bit different, and we'll talk a little bit more about some of the design differences and why I now have the Circle D stator and some of the stuff that I'm really excited about it here in a little bit. But this is just an example to show you. So this, as I said, is going to be in the middle of the pump and the turbine and the converter, and it is going to be on your stator tube of your transmission, which is not going to spin. And then, as I said, the input shaft is engaging with the turbine side of the converter. I will show you a picture of what that is as well, and maybe help you see a little bit better about how that actually works, and also the bearing system that Circle D has for that is a little bit better than some of the other options you can find, in my opinion. And they have done some testing and figured that out themselves as well. A lot of the other converter companies will use a bushing there instead of a bearing for the back of the turbine, and that bearing, you can just tell that's a better design right there. So that was something pretty cool. But anyways, to get into a little bit of how the converter actually functions, it is black magic. That's the end of it right there. Of course, I completely understand if you have that opinion. I have the same one only a few years ago before Pete had helped me understand how these actually work. Basically, what is happening in the converter, it is using fluid to accelerate the car. There is no actual friction in between any materials like you would have in like a clutch, unless of course you have a lockup converter. But this is not a lockup converter, and a lockup converter for a high performance application that's making 1,500, 2,000 plus horsepower is going to be very expensive. So that's not something that you're going to see very often, unless it's in something like a pro mod or something like that, where they can afford to spend $30,000 on a transmission and a converter. But obviously that's not the case here. We got a stock block LS, so I don't need my transmission and converter to cost 3 times as much as my motor does. So everybody or hopefully you know how a clutch functions. If you don't, then basically all that's happening is there are friction plates that are as you release the clutch, it applies pressure on those plates and starts to rub against the flywheel. And then once you are completely out of that clutch and it's no longer slipping, then it is completely mated to that flywheel, and you're going to have a 1-to-1 ratio of the RPM from the engine to the input shaft, and it's going to be 1-to-1 on the torque supplied through that as well. A converter is going to be a little bit different. As I said, it uses fluid to transfer that torque to the transmission. So there is no actual friction pieces like that. It's going to be using the pump side of the converter to send the fluid due to the centrifugal force out to the outer edge of the converter, and then it is going to get sent over to the turbine side of the converter. And whenever it is pushed into the turbine side of the converter, is going to be pushing on those fins on the converter, or on the turbine side of the converter, and that's going to be how you're transferring your torque from the engine to the input shaft. You can kind of think of it like, I'm sure you've sprayed like a ball with a water hose or pressure washer or something like that, or if you've done it with either one, you can tell the more pressure is going to move that more. That's the same aspect, that same theory kind of what's going on in a converter. It's using that fluid, pressurized fluid, to push the turbine side, and that's going to make it spin the same direction that the pump is trying to spin. Once it goes into the turbine side from the pump, it is going to return back to the middle of the converter, and then it is going to have to go back to the pump side. But before it does that, it's going to go into your stator. So as I showed you guys, this stator is going to be here in the middle of the converter on your stator tube, and the fluid is going to come back from the turbine and hit the stator, and it is going to get redirected back into the pump. And also, this is where the torque multiplication happens in a torque converter. I'm sure some of you have probably heard before that torque converters will multiply the torque. This is how they do it. Some of it, of course, is applied to the turbine from the pump, and then it is once again applying pressure to the pump, because it is the turbine, or the stator is redirecting the fluid into the pump, which is going to be pushing on the pump, helping that as well, while your engine, of course, is also the other part of the other part that is applying torque to the pump. So that is where your torque multiplication comes from. And then, of course, the fluid is going to go back through the pump and go and get sent back to the turbine side, and it's going to just repeat that process. And if you have more fluid in the converter, or I should say higher pressure in the converter, then it's going to try to couple harder. It's going to make it tighter, which, if you don't know what people mean when they say tighter or looser on converters, I will use an example of if you are on the trans brake in your car, or also it can be foot brake as well, but the foot brake is going to be a little bit different, because a lot of times you will overpower the power of the braking system before you actually get to the limit of where the converter can stall at. The stall RPM is going to be where you are making as much power as you can, and the converter is no longer going to allow that engine to climb RPM anymore. It's going to be stuck at that stall speed. So, say you have a 3200 stall converter, then assuming that it ended up right where it was supposed to be, which can vary on a lot of different things, like the altitude that you're at, or anything like that. Even the weather can change it a little bit. Anything that's going to change the torque output of your engine is going to change your stall speed. Also, another thing that's going to make a big change in that is going to be turbos, for example, but we'll get more into that here in a little bit. Anyways, if you have a tight converter, for example, then on the trans brake, you may only be able to get up to 2000 RPM before you are no longer able to climb RPM anymore. That is, of course, because whenever you're on the trans brake, your input shaft is not moving, the turbine side of the converter is not moving, so the converter is kind of fighting itself, trying to spin that turbine, and it's not able to. So you're going to get to a point where you can't spin that pump any faster while you're trying to gain RPM. So a looser converter is going to be one that's going to allow you to reach a higher RPM with the same torque input into the converter. So if you say you had that same combination, that same engine and everything, that was only able to go to 2000 RPM on the trans brake, let's say you go to a much looser converter, then you may be able to get up to 4000 RPM before it stalls out. Now let's get into how that is affected with turbos. As I said before, anything that's going to change your torque output of the engine is going to change your stall speed. So a turbo is a pretty big change in your torque output, of course. That's why we run them, so we can make more power. So if you are trying to stall your converter up without your turbo on, you may only be able to get to 3,200 RPM or 3,000 RPM or something like that. But then you put your converter on and you put 10 pounds of boost into the motor, and you may be able to get up to 4,000 or 5,000 RPM, something like that. So that's going to be a big factor that changes how the converter is going to act. And that's why it's so important to get a properly spec'd converter so it works properly for where you are. And that's why if you ever do order a converter, which speaking of, I am a dealer for Circle D Specialties, and I would be happy to help you out with one. I've been working with Pete for a long time with customers, and we have a lot of happy customers, and I would be happy to help you out, or even, I'm not even going to sell you anything that you don't need. So if you think you may benefit, then shoot me an email or message on my Facebook page. That's down in the description, and I can let you know if I think you could benefit and give you some options there. So anyways, that's why it needs to be spec'd properly, because they're going to ask a lot of questions on what you're doing and what your engine combination is and what kind of altitude you're in and all that. That's because all of that will play a role in how the converter is going to act. Just like the rear gear will play a role, like I said in the last video, where I seen a pretty large difference in how the converter acted just by changing the rear gear, running the exact same tune-up. You can go back and check that one out if you want to. So it needs to be set up for exactly what you're going to be doing with it. You're going to want a different converter if you're doing something like no prep or something like that, where you may not be using a whole lot of power, or you may not be able to use a whole lot of power on that stuff. Whereas if you're running on radial prep or something like that, then you're going to want a bit of a tighter converter. Now let's talk a little bit about what makes a converter tight or loose. So there's going to be quite a few factors in that, but the biggest thing that's going to be able to change is going to be the stator, or that's going to be how a company is going to change how the converter acts mostly. Most companies, or I think all companies actually, are going to be using a factory mass-produced converter to start with. So this one, for example, is referred to in a few different ways, but Nissan 9.5-inch core is one of them, because this is actually a converter originally from a Nissan vehicle. I'm not sure exactly which one, and then the 9.5-inch, of course, is going to be on the diameter. Now, it may not be the exact diameter, and everybody kind of calls it different names. Circle D calls this converter their 252 millimeter converter. One of the things that you're going to be able to change how tight or loose a converter is going to be by that diameter. A larger diameter is going to make the converter tighter, just because you're able to fit more fluid in there to help with that coupling process, and also because the larger diameter, of course, is going to increase the centrifugal force that's throwing that fluid to the outside of the converter and to the other side. So that's one way that you can change it. This converter, a 9.5-inch or 252 millimeter, is going to be used mostly in like the 800 to 2,000 horsepower range. And then above that, you're probably going to go to something like Circle D has a 258 millimeter, which also can be referred to as like 10-inch or somewhere around that, 10.5, just depends who you ask. And then there's also going to be their 264 millimeter converter, which is a 11-inch converter. And that one is going to be more specifically for stuff that is making a lot of power or is going to be running on really good surfaces. So it can have a converter that's going to couple very aggressively or more aggressively. Whereas, something like I'm doing, I'm typically on no prep. Also, I'm going to be producing at the most maybe 1900 horsepower. I want something that's not going to be very aggressive on coupling and grabbing the motor real hard. So that's why I'm going to be running a 252 millimeter converter. The other factor that is going to make a big difference on how tight or loose the converter is, and is actually the biggest thing that can be changed in the converter by a converter company, since, as I said, they use factory cores from like Nissan in this example. So that means that the pump side of the converter and the turbine side of the converter are going to be the original Nissan core, or from the original Nissan core. The biggest change is going to be the stator. However, they can make some slight modifications to the pump and turbine, and sometimes we'll make some modifications in order to strengthen those, and also can make some slight changes with some bends and things like that in order to make the pump and turbine side function a little bit differently. But the largest part that they're going to be able to change the function of the converter with is going to be the stator. So the stator's job not only is to redirect that fluid and push it into the pump, but it's also going to be to limit how much fluid goes from the turbine to the pump, and that in turn is going to limit how much fluid there is in general in the converter, and that's going to change how much torque it's going to require to meet a certain stall point. So that's going to, of course, change how tight or loose your converter is. So I actually have a couple stators here to give you an example. So this stator right here is, of course, my previous stator, and that is going to be for a 377 cubic inch engine that is on methanol, and it's a pretty efficient deal with some pretty nice heads, so it makes pretty good power. So I need a a fairly it would be on the tighter side of the stator in order to keep the engine RPM where we want it with the amount of torque that it produces. And then I have on the complete opposite end of the spectrum, I actually have my old stator from my stock bottom end 4.8, and this is actually the stator that was in my converter whenever I set the stock bottom end 4.8 record, which was, of course, 471 at 149 miles per hour. So as you can see, there's quite a bit of difference there. And what you will notice is that this right here is going to allow a lot more fluid through. So that's going to allow there to be more fluid in the converter, or more fluid flowing through the pump and turbine and the stator to assist in that coupling process and keep the RPM where we want it to be. So we don't want it to couple at too low of an RPM, and there's quite a few reasons that we don't want that I will explain a little bit more later, but we also don't want it to couple at too high of an RPM where we're not going to be able to get to the RPM we need before the converter starts coupling, and that's going to, of course, make us, you may have heard someone say like blow through the converter. That means that it's just not able to couple. And usually, or one thing with a converter is the higher RPM you spin it, the more it is going to couple up and drop that slip percentage. And whenever I say couple, I guess I should explain that. I mean, the speed difference between the pump side of the converter that is spun by the engine and the turbine side that is spinning the input shaft is going to get closer and closer until they are, as close as they can get. It's going to, and that's going to be your slip percentage. I'm sure a lot of you have heard that, and you have probably heard that that's a very important piece of a converter's function, which it is an important piece, but it is not quite as important as a lot of people think, in my opinion. And also there are a lot of factors outside the converter that can change that. Like I mentioned in the last video with the rear gear, the same exact stator, converter, everything had 23% slip with the 350 rear gear in the 8th mile, and then 7% slip with the 411 gear in the 8th mile. So that's one factor that can make a big difference. It wasn't that the converter was wrong for the 350 rear gear. It was that the gear was wrong for the 8th mile that I was doing. If I was running the car to the quarter mile like I had planned, then it would have coupled up much better as the RPM continued to climb and the drive shaft speed continued to catch up and get closer to what the drive shaft speed and also input shaft speed, turbine side of the converter, would have caught up to what the engine was doing and lowered that slip percentage. So of course the slip percentage is going to be the difference in the speed from the pump side of the converter or the engine to the input shaft side, the turbine. So anyways, as I was saying, you can see the big differences here in these. And these are not quite as advanced of stators as the Circle D one that I have now. I will actually attach some pictures to show you here in a minute, but you can definitely tell the difference on how much fluid one can flow versus the other. This one is going to limit fluid a lot more, so that means we can get to a higher RPM without requiring as much torque. And this stator right here would have not worked at all with the 377 cubic inch engine that I use this stator for. Just like this stator would have not worked at all for the 4.8. The 4.8, if I tried this stator, it would have been way too tight. It would have never spooled, wouldn't have even had a chance. And then, you know, if I still decided to run it, even though it didn't even spool, I would probably leave the line at very low RPM. I would have no boost, and I would be crawling off the line until the engine can finally make some boost. But the problem would come whenever it made the boost, then it would not allow the converter to flash up to a high enough RPM for the engine to be safe, making the amount of boost that it would. And that would cause a lot of issues, which I'm going to explain a little bit more later. And then if I were to use the 4.8 stator in the 377 cubic inch engine, then it would have been way too loose to where I would not have been able to apply any of the power from the engine to the input shaft, just because it would be making too much torque and not be able to, that converter wouldn't be able to couple properly. So anyways, one more thing that I will go over real quick while we are here before we go in and look at the data logs and show you some differences there and talk more about how it affects the engine and the safety of the engine. I will mention that I also have dump valves on this engine, or on this transmission I should say. And I actually have a two-stage dump valve kit. So one of those is going to be internal and one of those is going to be external. And these are also going to be able to change the function of the converter. As I said, you know, like I used the example earlier, if you use a water hose to push a ball and then a pressure washer, which one's going to push it faster and harder, or which one, you know, more pressure is going to apply more force to the other side of the converter, is going to make it couple better. So lower pressure is going to make it not couple as well, and that's going to allow you to increase your stall speed with the same amount of torque. So that's one way that we can change the stall speed of the converter without actually pulling it up, and pulling it out, I should say. And we can do that mid-run or while spooling, for example. That's where I use them the most, but we've also used them during the run as well. And how those are going to work is the internal dump valve is going to go and connect inside the transmission to the converter feed circuit of the valve body. So as I said, the converter is going to be spinning that pump. That pump is going to send fluid through the converter feed circuit, and then it's going to come into the converter. So that dump valve is connected into that circuit, and that fluid is going to run all the way up to this valve, this solenoid, until I open that solenoid. And if you open that solenoid, of course, it's going to let that fluid bypass, and it's going to bypass back into the pan. So that's going to lower the pressure significantly in that circuit, which is going to lower the pressure in the converter, and it's going to make it act much looser. So that's one way you can change how the converter acts during the run. I'm always using it for spooling. It's not necessary for me with the new engine. I can still spool just fine, but you know, you always want to be able to spool as quickly as possible. So that's something that I use every pass, and I can usually get to my target launch boost within 2 or 3 seconds. So you know, you don't want to be stuck having to take 6-7 seconds or maybe even longer to spool, especially when you're racing. If you ever get caught in a situation where maybe you're sitting in that first light and someone double bulbs you don't have a lot of time. You got to react to what just happened and then start spooling. So if your car takes 7 seconds and you're on a 7-second auto start, you're not going to be able to make it into the beams in time. So that's why I will always use that and try and make the spool time as best as possible. Also, the other dump valve here is going to be an external dump valve, and that is going to connect right here on the cooler circuit, which this is going to be the exit line of the cooler, which is actually going to come directly from the converter, because when the converter is doing its thing and using the fluid to couple, of course that is going to be putting a lot of heat into the fluid, because it's just a lot of stress on that fluid. So that is also why I'm sure you have heard that a higher stall converter is going to make your transmission get a lot hotter. That is true because of the fact that that fluid is just having more stress put on it in the converter, so it's going to get hotter. And especially whenever you are sitting there on the trans brake, that's going to put a lot of heat into the converter, because one side of the converter is spinning and the other is not. So that's really hard on that fluid. Also, a spragless stator is going to put some more heat in the converter because, of course, it is not going to be able to spin. So that is always going to be stationary. So the fluid is always going to be hitting a stationary piece in the middle of the converter, whereas a stator with a sprag or a mechanical diode is going to be able to freewheel in one direction, which will usually be happening when you are cruising. That way you do not make as much heat in the converter. However, if you have a good enough transmission cooler, you can run a spragless stator and still be okay. And also, same with spooling on the line, as long as you have good transmission lines and cooler and all that stuff, you will be okay, but you don't want to have to be stuck on the line spooling for a very long time, because that is going to put unnecessary heat. Anyways, back to explaining the external dump valve. That is going to be connected to that cooler circuit right there, and that's going to once again go straight to that solenoid. And then the same process there, whenever you open that solenoid, it's going to dump fluid from that cooler circuit back into the pan as well. And the way that that one is going to function is by taking some of the pressure on the exit side of the converter off, so it allows the converter to move more fluid out of itself easier. So typically that one is not going to be very effective unless you are already dumping the fluid before the converter. So both of those combined can have a pretty large effect, but the internal is going to have the largest effect, of course. So anyways, hopefully that explains some things for you guys. Now we will go inside and look at some data logs and compare that, and I will tell you how you can actually save your engine by having a properly spec converter, and also how you can have some pretty large performance gains by having the properly spec converter. Alright guys, we're going to go to the Circle D Specialties Facebook page to steal some of their pictures and show some of the differences and some of the cool things that they're doing with stator design, and show why I believe that they are ahead of the pack where as far as it goes with a converter technology. So here we are looking at a few different stator designs that they have come up with. Their stators, of course, are going to be a CNC'd billet steel piece. These stators are going to not have the outer ring welded to them yet, so that's why they're going to look a bit different than the ones that I showed to you earlier. Now those ones that I showed to you earlier are going to be a fabricated steel stator, so they are going to just have the fins welded into them, and those are just going to have a straight flat fin, where these, of course, you can see they have some different designs to them. So they can, of course, use their 3D modeling software and their CNC machine to do pretty much whatever they want with their stator designs, and they can also test them in their CFD software, which is computational fluid dynamics, which is going to allow them to see exactly how fluid is going to flow through the converter, which is going to tell them how it's going to function before they even put it in a car, so they can change designs and see exactly how it's going to work. So we can actually see some of these designs, some of the data from that software real quick that they have shared with us. You can see the stator here in the middle. You can see how that fluid is flowing through the converter, how it goes around the stator and all of that. And it's going to, they can use this data to change designs, as I said, and make the converter function differently. There's also a lot more data that they can get from this that they, of course, are not able to share, that is going to allow them to see how much torque it's going to require to get to a certain stall point, along with a lot of other data, including how much or what the torque multiplication of the converter is going to be at the different speed ratios and stuff, of course, which speed ratio is going to be the difference in speed from the turbine to the pump. So that's essentially going to be the same as slip. So this example here, they actually have at a speed ratio of 0, which is going to mean that the turbine is not moving, but the pump is. So you can see how the fluid is kind of flowing through the converter. And go to this other design, you can see some of the differences there. And then we can actually go to this last one. This is going to be a little bit closer to what kind of the stator that I had previously, that is going to be a flat vane. And you can see how the fluid is going to flow differently here. And you can actually see there's some turbulence here on this part of the stator, whereas on the other designs, it did not have that. So this is just part of why I think they're ahead of the pack as far as converters go. So they can use this data to change how the converter is going to run in all different parts of the run as well. In fact, we actually made some changes to how mine is going to work because mine previously was a little bit too tight down low, but it worked well up top. So they were able to make some changes that should be able to make it a little bit looser down low at the lower boost levels, and then it's still going to work like it needs to at higher boost. So I will show you guys the data log that kind of gives or shows you that example later on, but right now I'm just going to give you a comparison of two data logs that kind of show the differences in a better functioning converter and one that is too tight. So this top line, the solid line here, is of course going to be the looser stator, the looser converter, and this dotted line is going to be the tighter one, of course, because it is keeping the engine at a lower RPM. This dotted line is going to be from my 780 pass, where previously was the stock bottom end 4.8 record, to the quarter mile, and this solid line is going to be from a 751, which is actually the current stock bottom end 4.8 record, to the quarter mile, and I was very close to my 8th mile record in that pass as well. I'll put those slips up, of course. You can see there's quite a bit of difference in the RPM on these runs. Also down here I have the G meter data. My G meter for whatever reason has always read backwards, but since the data has always been like that, I've just left it that way. It is set up in the software and in the car properly, so maybe the stickers just got put on the wrong way or something, but the lower on the G meter is going to be more acceleration. So you can see the differences between the solid line and the dotted line, and you can pretty easily tell why that solid line was a faster pass than the dotted line, as we were pulling more G's nearly everywhere in the run, other than of course here where I lifted off the throttle for a little bit and then got back in it for a little bit and then lifted again. So that's why the mile per hour was a bit low on that 751 pass. But anyways, so you can actually see here early in the run, you can see some of the differences. We'll just start out with the launch RPM. There's a little bit of difference there. And then here early in the run, you can see that the RPM traces were very close to each other up to about this point. And if you look at the G meter, you can actually see that the G meter was very closely following itself there as well until this point. This is where they kind of separate the most. And you can see the solid line starts accelerating harder than the dotted line. And you can also see that the solid line is allowing the engine to get to a higher RPM in that same area. So we will go a little bit farther into the run here. You can see also the differences in how the RPM trace looks. This solid line, of course, is going to be a much smoother graph. There is a little bit of a dip here. I believe that may have been a little bit of a tire spin or just possibly something with the engine that caused it to produce a little bit less power in that point right there that made it dip down. That wasn't a thing with the converter function, but this dotted line here, you could see it's kind of climbing, and then it grabs it pretty hard and just flattens it out and actually drops the RPM some here. Like you can see it's 6640 right there, and then 6591 right there. So it actually grabbed the motor and pulled the RPM down some, and that is not really beneficial, of course. And you can also see the differences in the RPM here. So there is nearly 1,000 RPM difference right here in the run. So being 1,000 RPM different, of course, is going to make a pretty big difference, especially with an engine combination like mine, where it is a 4.8 liter with a very large cam, some pretty good flowing heads and all that. It's a combination that's going to want to spin pretty high RPM, and it's going to make more power at higher RPM. So if you that's one of the factors to take into account. So you can definitely see how the looser converter would be very beneficial for this combination, keeping the RPM up higher where we're making more power. Also, we'll note on this spot right here that you see there's a little bit of a bump there. You can also see the same thing down, there's a little roughness down here in the G meter. That was actually a little bit of a wheel spin right there. I believe we just had sat the front tires down and the car moved a little bit, so we had a little bit of spin right there, so that's why there was that little bit of a spike.
So I actually forgot that I had a video of this until I was editing, but you can see in this clip from inside the car that it wheelied a little ways out, and I was going to the left, so I turned the wheel just a little bit, but not too much because I knew the front tires were in the air. And then when it sat the front tires back down, you see the car turn, and you see the GoPro shake a little bit. It's shaking because the car started to spin some. So that's the spot we see there in the data log and on the G meter.
Anyways, we will go now to the shift points in both of the runs. So this solid line is going to be 8,300 RPM shift point, and then we will go to the dotted line, and let's see, that is 8,260, so very close on the shift point. Then we will go to where the converter dropped to after the shift on the solid line. Let's see what the lowest point here is. That is looks like about 6750 there. And then on this dotted line, we went from 8260. Let's see, the lowest point here is about 6700 RPM. So that is a pretty large difference there. And that is a good place to mention. This is where you can very easily hurt an engine, and that's going to be any engine, but more specifically a stock bottom end engine is going to be even more prone to getting hurt in this area. The reason for that being that the more torque that you make, the more cylinder pressure there is going to be, and so if you're at a lower RPM making the same power, you're going to be making a lot more torque, a lot more cylinder pressure, which is going to mean you're going to run into lifting heads, bending rods, things like that sooner than if you were at a higher RPM making the same power. And just to give you an example of that, we'll take these RPMs that we ended up at after the shift and assume that we're making 1250 horsepower at that point. So if we were making 1250 horsepower at 7,600 RPM from the solid line where we dropped to, that is going to be 863 foot-pounds of torque. Whereas if we were making that 1250 horsepower at 6,700 RPM where we dropped to with the converter that was too tight, that is going to be 980 foot-pounds of torque. So that is a huge difference in torque there. And of course, the engine was able to take that torque with the, of course, this is also just kind of estimating what it was making, because we're not going to be making the same power across the entire RPM band, and also I'm going to be pulling some timing at lower RPM to make less power so we can get that torque number lower. But assuming that we were making 980 foot-pounds there, if we were to make that same 980 foot-pounds at the higher 7,600 RPM from the looser converter, then that would be nearly 1,420 horsepower. So there is a huge difference there. And of course, if we're making the same amount of torque, then we're putting the same amount of stress on the engine, at least on the internals and things like that. Of course, there are some things that you could run into, some issues you could run into by too much RPM, but typically you're going to run into issues from too much torque before you are going to run into issues from RPM. And this right here, that is exactly why I say that converters are so important. And you will often hear when it comes to stock bottom end stuff, the first thing everybody says is you have to have a good tuner. Well, in my opinion, the tuner is not as important as the converter, and that's coming from a tuner that has a stock bottom end record. So yeah, you definitely cannot out-tune a crappy converter. You really can't out-tune a crappy combination in general, but converter is a very large part of that. And you could have even I think there's just more room that you could miss with a tune than you can on a converter. Of course, if you are too aggressive with a tune-up and detonate the motor, then that's not going to get you very far. But in the same realm, if you have a perfect tune and too tight of a converter where it drops the RPM real low, then it's going to hurt the motor, even though that tune-up was as good as it could be. You could take my same tune-up where I set the record with and put it put a a very tight converter in it and blow it up the first pass, and you wouldn't have even been going as fast once you got to that point of the pass anyways. So this is a part of why a converter is so important to function exactly how you need it to. All right, so now I'm going to show you where we came up with the idea to loosen the converter up a little bit down low. This is going to be a pass from slicks and no prep, or light prep from the forged engine combination that I had. So you can see down here the converter, it doesn't flash real high RPM down here at this lower boost level, and of course we have a very slow boost ramp due to the fact that we're on a not an ideal surface, but you can see up here, the converter doesn't drop a whole lot of RPM. You see there we're dropping from 7820 to 7370 right there. So the converter is working pretty well up here at this higher boost. We're about 30 pounds of boost right here, but down here at this lower boost level, we're leaving on 7 pounds of boost, and now only at the 60 foot we're at about 20 pounds of boost or so, and that's a 119 60 foot. So that's getting after it decently to the 60 foot, and the converter is not quite flashing as high as I would like to there, which we could change that with the dump valves, of course, but also it would be I would prefer if we could change that with the converter itself, and then also have the dump valves if we need to make some more changes there. So that's something that Circle D is going to be able to do. So I'm really excited about that, and I'm excited to try those out. So hopefully you guys enjoyed the video. If you made it this far, I appreciate it. I know this is a very long video. Anyways, if I can help you guys with anything, let me know, and we'll see you in the next one talking about the engine.